The final topic for this course is what I'm about to do right now, the Gram-Schmidt orthogonalization. And we've spent a lot of time preparing for just this particular moment. Well, let's go ahead and get to the theorem, and then we'll do some examples to illustrate it. So this theorem is the Gram-Schmidt theorem. And here's what it says. Let W be a subspace of Rn with basis U1 up to UP. Define V1 equals U1, V2 equals U2 minus U2 dot V1 over V1 dot V1 times V1. Then I'm going to create V3 that will equal U3 minus U3 dot V1 over V1 dot V1 times V1 minus U3 dot V2 over V2 dot V2 times V2. Hopefully you can see the pattern by now. Let me do one more just so we know where we're going. V4 will be U4 minus U4 dot V1 all over V1 dot V1 times V1 minus U4 dot V2 over V2 dot V2 times V2 minus U4 dot V3 all over V3 dot V3 times V3. And you can keep going on and on. Hopefully you see the pattern by now until I finally get to VP, which equals UP minus UP dot V1 over V1 dot V1 times V1 minus dot dot dot, and that goes all the way until you get to UP dot VP minus 1 over VP minus 1 dot VP minus 1, make that dot better, times VP minus 1. So you use, basically you're using, as you develop the vectors, then you develop the next vector based on previous vectors. So here's the big result. Then V1 up to VP is an orthogonal basis for W. Additionally, the span of V1 up to just VK equals the span of U1 up to UK for any K between 1 and P. So there's the big deal. I want you to understand what we're doing here. We're starting with a subspace of Rn. W is any subspace. From that, I'm going to be able to take a basis for it and turn it into an orthogonal basis. You saw how many computations were simplified by that. So having an orthogonal basis is very useful. So I can create an orthogonal basis, and not only that, the span as I create them will stay the same as the span of the u's up to that point. So the span of v1 will equal u1, the span of v1, v2 will equal the span of u1, u2, etc., and etc. So for the proof, if you're familiar with mathematical induction, then you'll probably recognize what we're going to do in this proof, because the steps are a lot like, if not identical, to what you would do for mathematical induction. But anyways, let me take my k anywhere between 1 and p. Let w sub k equal the span of u1 up to uk. Since v1 equals u1, that's the first step in this definition here. Let me remind you, v1 equals u1. Since that's the very first step there, we know that the span of v1 equals the span of u1. Now, assume that for k less than p, that the span of v1 up to vk equals the span of u1 up to uk. So this is where the induction hypothesis is occurring. We showed that it's true for k equal 1 right here. When k is equal to 1, these two things had the same span. Now I'm going to assume that it's true for some k less than p, and then I'm going to show that it's true for k plus 1. So then, let's take a look at what we have. V sub k plus 1 equals u sub k plus 1 minus the projection onto w sub k of u sub k. So I made a mistake right here. That's wk plus 1. Goes into that spot there. Now then, what do we have? uk plus 1 equals the projection onto wk of uk plus 1 plus uk plus 1 minus the projection onto wk of uk plus 1. Now if you'll see, what we have here is this here is in w sub k. So this right here has to be in w sub k perp by the orthogonal decomposition theorem. We know that we can write it uniquely in that fashion, so that forces this part here. Remember, uniquely means that this part here was unique. That means this part right here was unique also. So we know that this part right here, or vk, is in w perp. So that is v sub k plus 1 is in w sub k perp. Now, the projection onto wk of uk plus 1, remember that was uk plus 1 dot v1 all over v1 dot v1 times v1 plus dot 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 plus all the way up to uk plus 1 dot vk all over vk dot vk times vk. Notice that that is in the span of v1 up to vk, which we know equals w sub k by the induction hypothesis. And automatically that's a subset of wk plus 1 because wk plus 1 will add an extra basis vector. So all I'm getting at from all of this is that the projection of w sub k uk plus 1 is in wk plus 1. Next, u sub k plus 1 is in wk plus 1. Remember, that was the last basis vector added to wk plus 1. So that implies that v sub k plus 1, which, where was it up there? Maybe I should write it again just to be on the safe side. That equals uk plus 1 minus the projection onto w sub k uk plus 1. Let's see what all we have here. uk plus 1, where are you at? Was in, there it is, wk plus 1. So this is in w sub k plus 1. And then we showed this part was also in w sub k plus 1. So that tells me that v sub k plus 1 is in wk plus 1. V sub k plus 1 is not the zero vector because u sub k plus 1 was not in the span of w sub, well, the span of the u, sorry, not w, but the span of the u1 up to u sub k, which equals w sub k. Remember, this is the definition of w sub k. U sub k plus 1 was another basis vector that we added to this thing to make a larger basis. So we definitely know that u sub k plus 1 was not equal to 0, but more importantly, I want v sub k plus 1 not to equal 0. But anyways, u sub k plus 1 is not in wk, but the projection onto wk, u sub k plus 1 is in wk. So v then, where did you go? V is made up of an element not in wk minus an element in wk. There's no way that it could be equal to 0 since it's in those two different sets. Now, we already know this breakdown right here, u sub k minus 1 minus the projection onto wk of u sub k plus 1. We already know that this is perpendicular to w sub k. So we know that v sub k plus 1 is in wk perp. This, of course, implies that v1 up to v sub k plus 1 is an orthogonal set of non-zero vectors in w sub k plus 1. Well, w sub k plus 1's dimension is k plus 1. And here is a set of linearly independent vectors. If it's orthogonal, then it's linearly independent. So since v1 up to v sub k plus 1 is a linearly independent set of non-zero vectors, well, linear independent set of k plus 1 non-zero vectors, in wk plus 1, and the dimension of w sub k plus 1 equals k plus 1, we must have that w sub k plus 1 is the span of the vectors v1 up to v sub k plus 1. That finishes off the induction proof. And so when you get to k plus 1 equals p, you're done. As an example, let's see, we're going to let u1 equal 0.42 and u2 equal 5, 6, negative 7. Use Gram-Schmidt to construct an orthogonal basis for W, which is the span of U1 and U2. So we want to construct an orthonormal basis for that. That's where we're going to construct V1 and V2 that are orthogonal and they span the same space. So according to the process, V1 equals U1. So we're halfway done. V2 equals U2 minus U2 dot V1 over V1 dot V1 times V1. 5, 6, negative 7 minus, now let's see, I needed to U2 times V1, which is U1, okay, so U2 times U1 dot U1, so 5 times 0 is 0, 6 times 4 is 24, minus 14, so that'll be 10, over V1 dot V1, which is U1 dot U1, so that's over 1620. And then V1 was U1, 0, 4, 2. And let's see what we get then. I have 5, 6, negative 7. This is just 1/2, so I get minus 0, 2, 1. And what is this going to equal? I have 5, 4, negative 8. And so our orthogonal basis well, U1, we're going to keep that one, but then we throw out U2 and exchange it for V2, and we get 5, 4, negative 8. As a quick check, just ensure that they are orthogonal. So 4 times 4 is 16, 2 times negative 8 is negative 16. You can see that they will cancel each other out. For our next example, create an orthonormal basis for the previous example. And all we have to do there, it's already orthogonal. All we have to do is change all their lengths to unit lengths. So when I take the norm of 0, 4, 2, what do we have? The square root of 0 squared plus 4 squared plus 2 squared. That's the square root of 20. And then for the other one, we have 5, 4, negative 8. That equals the square root of 5 squared plus 4 squared plus negative 8 squared. And that is equal to 25 plus 16 is 41 plus 64 is 95. And so my orthonormal basis, it's exactly the same thing except you just divide by the lengths. So I will have 1 over the square root of 20 times 0, 4, 2. And then I had 1 over the square root of 95 times 5, 4, negative 8. And there is our orthonormal basis. For our next example, let's let u1 will equal, looks like we've got 4 vectors. So I've got negative 1, 3, 1, 1. u2 will equal 6, negative 8, negative 2, negative 4. And u3 will equal 6, 3, 6, negative 3. Create an orthogonal basis for W, which is the span of those vectors. So as before, let me put the solution here. V1 equals U1. That's always the easiest one. And the next one, V2, that equals U2 minus U2 dot V1 over V1 dot V1 times V1. Let's see what that's equal to. U2, I'll put it in there. So let me put U2 in there. 6, negative 8, negative 2, negative 4, minus, let me see, U2 dot V1, or that'd be U2 dot U1. So 6 times negative 1 is negative 6. 3 times negative 8 is negative 24, so I'm at negative 30. Then I have negative 32, then I have negative 36. And then I need to do V1 dot V1, which is U1 dot U1. So I have 1 plus 9 plus 1 plus 1 is a total of 12. And let me put my V1 in here, or U1. Negative 1, 3, 1, 1. And let's see what all we get for this. I'm going to get 6. Now right here will be positive 3. What I'm going to do, let me just make this a little simpler on myself here. I'm going to change this to just a 3, and I'll make it a plus. It'll make it so I don't screw up these simple operations. So let me do this again. 6 minus 3 gives me 3. Then negative 8 plus 9 gives me 1. And then negative 2 plus 3 gives me 1. And then negative 4 plus 3 gives me negative 1. So there's my V2. And then I'm ready for the last vector. I'll give myself lots of space here, V3. So that'll be U3 minus U3 dot V1 over V1 dot V1 times V1 minus U3 dot V2 over V2 dot V2 times V2. All right, let's put these numbers in. What's my U3 equal to? 6, 3, 6, negative 3. So 6, 3, 6, negative 3. Minus, now I have to do U3 times V, or dot V1, and V1 was U1. So let me do that first. U3 dot U1. So I get 6 times negative 1. I'll get negative 6 plus 3 times 3. So negative 6 plus 9. I'm at 3 so far. 3 plus 6 will give me 9. Then minus 3 will give me 6 again. Now V1 dot V1 it was over there somewhere. I got rid of it, didn't it? But I believe it was 12. Yes, it was 12. And then let me put the V1, which was U1, negative 1, 3, 1, 1. And then minus, and then U3 dot V2. So V2 is over here. There's V2. Now where's my U3? There it is up there. So this vector dotted with this vector. So U3 dot V3. Let's see what happens. 6 times 3 is 18. Plus 3 times 1, I'm at 21. Plus 6 times 1, I'm at 27. Plus 3, so I'm at 30. Divided by V2 dot V2. So let me do V2 dot V2. Say 9, 10, 11, 12. And that one there times V2 was 3, 1, 1, negative 1. And when all is said and done, I'll let you do the check on this one. We get negative 1, negative 1, 3, negative 1. So my answer then, W equals the span of these vectors. What were they? Negative 1, 3, 1, 1. Oh, I forgot how long my vectors were. These are 4 vectors, not 3 vectors. So, comma. What was the next one? 3, 1, 1, negative 1. 3, 1, 1, negative 1. And then finally, for the last one, negative 1, 3, negative 1. So what I want to do is make sure that they're perpendicular. I know they are, but let's just check it. Negative 3, I'm doing the dot product, the first 2 vectors. So negative 3 plus 3, 0. 1 minus 1, they zero out. Good. So negative 3 plus negative 1 is negative 4, plus 3 is negative 1, plus 1 zeros out. Now finally, the first vector times the or dotted with the last vector. So negative 1 times 1 is 1, plus 3 times negative 1. So 1 minus 3 is negative 2, plus 1 times 3. So negative 2 plus 3 is 1, and then 1 minus 1 is 0. So it's orthogonal. And then you may be able to guess this last example. Construct an orthonormal basis for W in the last example. So all I have to do is divide by the lengths of each of these things, and we'll get the following. W equals the span. And let me get the lengths of these vectors then. Here, I know that the length of this vector was 12. I've done it a few times already, so I have 1 over the square root of 12 times -1, 3, 1, 1. So now it has length 1. The next one. Well, notice they're all the square root of 12 because you have 1, 3, and 4 1s. It doesn't matter if they're negative or positive. When you square them, that'll go away. So it's going to be 1 over the square root of 12 times 3, 1, 1, -1. And then 1 over the square root of 12 times -1, -1, 3, -1. And that concludes the material for the course.